Let's use our properties that we've learned about the logarithm and writing between logarithmic and exponential form in order to solve for the value of x in each of these 9 different examples. Remember, we defined the logarithmic function in another video clip, and then within that clip also talked about switching between logarithmic form and exponential form. If you haven't viewed that and aren't sure how to do that yet, go back and find the video clip that talks about the logarithmic form and the exponential form and the definition of a logarithmic function, and then come back and try to find these. Okay, so let's look at these values. For each of these, I want to either think through the process if I have all of the values on the side with the logarithm to find my value of x, or I want to write this in exponential form from the logarithmic form in order to help me solve for the value of x. So let's start with the first one. Remember, logarithms are the exponents that you put on the base to create the value that you're taking the logarithm of. So this first one asks, what exponent will I put on 2 to create the value 8? Well, 2 to the first power is 2, 2 to the second power is 4, and 2 to the third power is 8. So the exponent I put on 2 to create the value of 8 is 3. So my x is equal to 3. And that one we could just kind of work through thinking through the process. When I look at this next example, log base x of 125 equals 3, it might suit us better to write this in exponential form and then solve it. So remember, logarithms are the exponents you put on this base in order to create this value. And in this particular equation, it tells me that the exponent I put on the base to create that value is 3. So my base is x, my exponent on my base is 3, and I'm supposed to create the value of 125. Now, as you see, when I write it from the logarithmic form to the exponential form, I have an equation that I can solve just by taking the cubed root of both sides in this particular example, and we'll get the cubed root of x cubed is x, and the cubed root of 125 is 5. So we get x is equal to 5, because 5 to the third power would create the value 125. Our next one is log of x is equal to 4, and there's no base showing here. Remember, when it's spelled L-O-G and there's no base that's showing, the assumed base is base 10, and those are called common logs. So here, I've got an exponent I'm going to put on 10 to create x is the exponent of 4. So again, we'll write this one in exponential form out of the log form. My base is 10, the exponent on my base is 4, and that gives me the value of x. And so it's really nice in this form because then it's already solved for. I just need to take 10 to the 4th power. Well, 10 to the 4th power is 10,000. So my x is equal to 10,000 in this third example. In our fourth example, it's spelled ln instead of log, but again, there's no base showing. Remember, when it's spelled ln, that's the natural log, and the assumed base on the natural log is a base e. So writing this out of the logarithmic form into the exponential form, I've got my base of e, my exponent of 9 is what I will have to create that value of x. And since this is a fairly large number, we're just going to leave this as x is equal to e to the 9. And not only because it's larger, but also because if I go to a decimal and I try to give a decimal approximation for it, I no longer have the exact value. I only have the decimal approximation. So we want to leave this exact unless we have directions otherwise in the setup of the problem that tells us to round it. Okay, our fifth example, again, remember, if it's spelled ln and there's no base showing, the base is e. So here we have my base of e to the power of x is equal to e to the 7th, this quantity. And on both sides of this equal sign, I have a base of e, and they're both raised to a power. So if this is truly to be equal and my bases are already equal, then my powers have to be equal. So x must be 7. We'll actually learn a property of logarithms in another segment that will help us do this exact same question in a different way. But we'll get the same answer. So whichever way makes sense to you is the way you want to go through it. Okay, example 6. Log base 5 of x is equal to -2. So the exponent I put on 5 to create my value of x is an exponent of -2. My base is 5, my exponent's -2, and that's how I get my value of x. And then remember, negatives on my exponents reciprocal the base or go in the denominator of the fraction. So I have x is equal to 1 over 5 squared. When I take it to the denominator of the fraction, the negative comes off the exponent. And then that gives me 1 over 5 squared is 25. So my x in this equation is x is equal to 1 over 25. Now example 7, we're going to do the same process. So we have our base of x raised to the first power is 7. Well, that's just x equals 7. In the next one, I have my exponent on 4 to give your value of x is 0. So I put the exponent of 0 on my base of 4. 4 to the 0 gives me x. So x is equal to, well, any non-zero number to the 0 power is 1. And then the final example for this segment is log base 8 of x is 1/3. So the exponent I put on 8 to create my x is the exponent of 1/3. 8 to the 1/3 power is how I'll get my x. And remember, with fractional exponents, the denominator of the fractional exponent is the index of your radical. So this is really just asking you for the cubed root. The index of the radical is the denominator of your fractional exponent. It's just asking you for the cubed root of 8, it's your x, and the cubed root of 8 is 2. So x is equal to 2. And so there are 9 different examples of working with going from logarithmic form to exponential form if necessary in order to find the unknown values of x.